Hello everyone. On behalf of ISI Bangalore students and researchers, I welcome all of you to the third day of Limit Camp. Today's speaker is Saraswata Sensarma. He has done his BMath from ISI Bangalore and now he is doing his MMath from ISI Kolkata. He is interested in probability and stochastic processes, especially in models arising from statistical mechanics. I will be welcoming the speaker for his talk titled Look Out for Lookalikes, Counting What Really Counts. This talk will be recorded, so you can go to our YouTube channel and check it out later. Please keep your microphone off during the talk. You can ask questions in the chat. I'll hand it over to you, Saraswata.
Thank you so much, Rinkini. So I'll start. And one note, don't worry about taking notes. I'll send this entire PDF because there are loads of pictures here, which it's hard to take a note of. Anyway, so the title is Look Out for Lookalikes, and you want to avoid double counting basically, or multiple counting. But let's go one by one. Let's start with a problem. Okay. So in how many ways can we color the vertices of a square using red and blue colors? We have a square and we want every star is either red or blue. Well, this is one of the first problems we ever see, and we have two choices for each vertex, so there are 16 of them. Let's make it slightly harder. What if I say that rotations are not different? In particular, what I mean is if I take these four configurations, by the way, I hope my cursor is visible. Yeah. So if I look at these four configurations, they are the same thing. This happens in the case of many real world objects. For example, Rubik's cubes or like compounds, organic compounds. There are many representations of them, but there are multiple representations corresponding to the same object. All of these four correspond to the same thing. We will consider them as the same. And however, these two, there's no way to rotate one into the other. So these are genuinely different objects, but these are not genuinely different objects. So now the question is, how many genuinely different objects do we have? In our case, it's not too difficult. You can just sit and figure it out just by a little bit of case bashing. That there are 6 of them. Obviously, if the number of reds and blues are different, there's no way to get rotate one into the other. So if you have all blue, this is the only option. If you have all blue but one red, this is the only option. 2 reds and 2 blues, you would find 2 options. And correspondingly, for 3 red and 1 blue, there's 1 option. And all 4 reds, this is the only option. So in this case, it was not too hard to sit back and just compute it out. Just look at it and try and visualize. But the question is, in general, it might be much harder. I can replace the square by a heptadecagon, 17 gone, and it would take days to figure that out. Let's look at another example. The counting the number of isomers, so you take a benzene ring, and what I say is you attach one CH3, one methyl group, and one OH, one alcohol group. Okay. So, and I ask how many compounds can you make out of this? Well, and I just make this extra thing that you cannot attach them at the same site on the benzene ring. Well, the way to count them would be, okay, so you have 6 positions. You put CH3 in one of the positions, let's say, so there are 6 choices for CH3, and AJ and this OH, you put it another position. So remaining 5 positions, there are 5 choices for OH. Very well. But now this is a real object, a real compound, and these guys, all of them are representations of the same compound. You can, of course, in real life, you can take a compound, flip it, it doesn't change anything. So all of these are representations of the same object. So if we wish to count the number of organic compounds arising in this fashion, we have to take care of these redundancies, right? Well, as it turns out, the number of different organic compounds here are exactly 3. You can fix OH in one position and look at CH3 at a distance 1, 2, or 3 from it. But again, this is a very special case. If I give you a huge protein, it takes time to figure it out. Exactly how many different configurations can you get? So this is our problem basically. We have representations of a given object. The number of representations is typically easy to count. For example, if you look here, it was 6 times 5. That's easy to count. It's just 6p2. Similarly, if we go back here, the number of representations, the total number of squares was easy to count, 2 to the power 4. Typically, the number of these representations will be easy to count. Representations, I'll call them figures, okay? So number of these figures would be easy to count, but multiple figures can correspond to the same object. So how do we count the number of objects and avoid this nuisance of double counting? That will be the idea of this talk, okay? All right. So let's get back to the more quote unquote mathematical problem, moving away from chemistry. So, well, what is our previous problem? We have a set of figures as just described, uh, which is this. So there are 16 figures over here, and we have this collection. We'll call it a group of symmetries. Group right now is in quotes. I'll describe what a group means later on, but for now, just treat it as a collection of symmetries. Okay. So we have this group of symmetries, which is rotate by 90 degrees. Do it twice, so they rotate by 180 degrees, rotate by 270 degrees, or do nothing. These are the 4 things that we can do. I'm representing do nothing by E, and that actually turns out to be a standard notation. Okay. So there are these 4 operations you can perform on any figure. So if you take any figure, rotate by 90 degrees, you get a different figure. All right. And we'll denote this by G dot X. You take G from here, G from this group of symmetries, G for group, and X, any figure. Then G dot X denotes the operation of G on X. For example, if you want to rotate this particular picture by 90 degrees, what you can do is you can grab the picture, make a copy, and rotate it by 90 degrees. And yeah, in accordance with all mathematical notation, rotation by 90 degrees means in the counterclockwise direction, in the anti-clockwise direction, this way. Okay, this way. All right. So yeah, that's now the question is, how do we count the distinct objects? Before that, let's get to a small definition. Let's analyze this case further without actually worrying too much about our problem. But let's analyze this particular situation. But before that, let's make a definition. For G in G, fix a symmetry. Okay, it might be rotation by 90, rotation by 180. Fix a symmetry and define this set. This set X power G, as I have written out, I'll be calling it, X fix G. Okay, X fix G is a set of all figures which remains unchanged upon the action by G. There is G dot X, G applied on X remains X. For example, if I take this figure, rotating it by 180 degrees does not change it. So this is an element of X. So this guy is an element of X R180. All right. So you have XG for 4 Gs. G can be do nothing, rotate by 90, 180, 270 degrees. So let's figure out what those are. If I ask you what is XE, what are the figures which remain invariant under doing nothing? Well, every figure. So XE is just X. It's the whole set. It's a set of all figures. And the cardinality hence is 16, as we had before. If we look at operation, if we look at this rotation by 90 degrees, then there's something fun arising. See, this is the original picture. This is the original picture, and this is the rotated picture. In the rotated picture, if these two are supposed to be the same, then C1 has to be C4, C2 has to be C1, C3 has to be C2, and C4 has to be C3 for the two of them to be the same. In particular, all of them have to be the same. C1 equal to C3 equal to C3 equal to C1, C2, C3, C4 all are same, which means, by the way, Ci represents a color at each vertex. So all the colors must be the same. In particular, the only possibilities are these two. All right. This is our set X R90 and the cardinality is 2. If you look at rotation by 270 degrees, it's exactly the same thing. It's just going in the opposite direction. Again, we have exactly these two. Rotation by 180 is a little bit more intricate because if you rotate, you would realize that this guy upon rotation by 180 goes to this guy and this guy comes back here. So these two have to be the same. So these two have to be the same and these two have to be the same. Working example, if you go back to the example we discussed here, that's precisely the case. So this solid color we can choose in two ways, and this transparent color we can choose again in two ways. It could be red or blue. So that gives four possibilities. So we have 16, 2, 2, and 4. And just for the fun of it, let's just add them together and take an average for no reason at all. So you're looking at this. This is the average number of symmetrical pictures. Okay. This is a this is the number of symmetrical pictures with respect to identity and so on. And this is just the average number of symmetrical pictures. And as it turns out, lo and behold, this is 6. And 6 is precisely the number of objects that we had, the number of distinct, rotationally distinct figures.
So I had a doubt. Uh,
Yeah, go on.
in the operation by 180, if we choose one of the colors, is it the
Sorry, can you repeat
other
once?
in the 180 when we rotate by 180 degrees? If we
Yeah,
choose one of the colors, example for it, then doesn't the other one get fixed by itself?
your voice is cracking actually. In
Am I
this
audible
one
now?
by, yeah, go on.
I'm saying in the 181, if we choose one of the colors, isn't the other one fixed by itself? Like because they don't have to be different colors.
No, no,
So
no. They can be the same. Uh, all that is like this is also preserved by 180, right? Rotate by
yeah.
180, this guy is also preserved. So you have genuinely different choices. You can
Oh,
choose 2 and 2, right? I colored it this way so that just to say that the blacks have to be the same and these two transparent ones have to be the same. But the black and transparent one could be same as well. That's not a problem. Okay.
Sir,
okay.
All right.
uh,
So,
sir,
as, yeah, go on.
sir. So this is the reason why the cardinality for XR180 is 4.
Yeah, because you have these two and as well as you have these two like red, red, blue, blue and also blue, blue, red, red. Okay.
Okay.
So you have these two extra ones. So that's why the cardinality is 4. All right. So as it turns out, this procedure works always. And our goal in this talk will be to sort of figure out why this works. And if we go back, this is colloquially known as Burnside's lemma, this procedure that I said. But originally it was published by Cauchy in 1845, and the dates are a bit wrong. So I'll correct it. And later on, it was published, I believe, independently by Frobenius, or maybe they knew because at that time, like they had a lot of private communication. So we don't know whether one knew and the other didn't. Frobenius also used it in his work in 1887. It was later on published by Burnside in his book of group theory around 1911. But this was one of the first times people saw it used in a book, which was mainly which was popular. So it just came to be known as Burnside's lemma. Uh, More recently, people call it Cauchy-Frobenius theorem, but I'll just stick to Burnside's lemma. Okay. So, well, we had our fun with our first example. Let's look at another one. And this is a one which is slightly bigger, so it's more it's harder to compute by hand. So we wish to count the number of fully filled tic-tac-toe boards, katakuti boards, up to rotations and reflections. So a fully filled board looks like this. It has 5 X's and 4 O's, knots and crosses. And we don't care who won or who lost. Okay, we just want to fill up the board. This is not the game tic-tac-toe. We are just filling up the board of tic-tac-toe. And now we have allowed for more equivalences, right? We have said up to rotations or reflections. So there are 3 rotations. Doing nothing is also okay, maybe a rotation. And there are 3 reflections other than that, as we had seen before. And also there are these 4 reflections. You can reflect along this axis, along this diagonal axis, this vertical axis, along another diagonal axis. So there's a lot more to count, but the procedure is exactly the same. Our set of figures is exactly this. It's X, which looks like, so there are 9 places to fill. Each place can be filled with a knot or a cross. All right. So that gives it, oh, I have a, oh, by the way, I meant different. Okay. This is not the case. This is wrong. This is wrong. Note that this is wrong. There can be any number of knots and any number of crosses. Okay, any number of crosses and any number of knots. It does not have to be the case that one player goes after the other. We are just filling it up. It's just a different coloring. Okay, so yeah, just sorry about that. So this is a much more extensive problem, and let's study it. Well, the total number of figures, you have 9 places you can fill with knots and crosses. So the answer is 2 power 9. That's something. How many of them? Now let's look at this more fixing, guys. How many of them are fixed under a 90-degree rotation? So if you look at a 90-degree rotation, the C goes here, A goes here, and these 4 outer ones cycle. The 4, so this guy goes here, this guy goes here, this guy goes here, and this guy goes here. These guys cycle, and the center remains exactly where it was. And if you want them to be equal, the 4 outer ones must have the same color. The 4 middle ones must have the same color, and the center can be any other color. So again, there are 2 cube possibilities. Again, I'm talking about colors, but what I mean is knots and crosses. But anyway, so there are 2 cube possibilities, 2 for each of them. If you look at reflections, this is for rotation by 90 degrees. Rotation by 270 is exactly the same. It's just the other way around. Again, yeah. So what about this reflection, this particular reflection? Well, these 2 have to be the same. For a figure to be symmetric under this reflection, let's see, we'll draw this. And if it's symmetric under this reflection, these two must match up. And the ones in the middle could be anything. So there are 1, 2, 3, 4, 5, 6. The black just denotes that there are no constraints put on them. Okay, it's not that they are all equal. There's no constraints on them. So there are 2 to the power 6 possibilities now. Similarly, if you look at S2, a reflection along this diagonal, again, these 2 must be the same, these 2 must be the same, these 2 must be the same, and the diagonal could be anything. So again, there are 2 to the power 6 possibilities. And finally, if you rotate by 180 degrees, this is slightly different. Then these 2 have to be the same. These 2, the vertically opposite ones, or antipodal ones. Yeah, antipodal is probably the correct word. The antipodal ones must be the same. So there are 4 possibilities on the outside, and the one in the center is just the one in the center. There's nothing to worry about that. Okay. So there are 2 to the power 5 possibilities. I hope there was no questions regarding this, but anyway, this is just sitting and figuring things out. There's nothing particularly mathematical going on here. But let's look at the same procedure again. Let's look at the average number of symmetrical figures. We had 8 figures here, 2 to the power 6 here, 2 to the power 6 here, 2 to the power 5 here. So if you add these up, in general, there's like fixed by identity, there are 2 to the power 9, many of them. This is 2 cubed, and similarly, this is also 2 cubed. And if you list them out, you get 102 symmetrical pictures. 102 distinct pictures. And figuring this out by hand would be, now we realize figuring this by hand would be quite a chore, because calculating 102 distinct pictures would be, and also here you have reflections and rotations and all things going on. So it will be much harder. But this procedure directly gives us exactly what those configurations are, or at least the number of the configurations. We'll spend the second half of our talk worrying about what the configurations are, but this gives us the number of configurations. So hopefully I've convinced you that this is a very powerful procedure. And now let's try and look at a proof of this. Before going to a proof, let's look at a slightly more formal setup. This X, capital X as usual, is the list of all figures, and capital G is a group of symmetries. So you have E and G1, G2, and so on. This is just doesn't like, it's just a list. Don't worry about it. Both are finite. Okay. Otherwise, makes no sense to ask. We only count finite things. And let's look at. Oh, by the way, I can shorten this. Yeah. Let's look at this list of figures in a slightly different light. Here are 16 figures, and we look at these transformations. For example, this guy upon rotation becomes this guy, which upon rotation becomes this, which upon rotation becomes this. So you have this by action of this group, by multiplying rather, acting upon X by elements of this group, we can take it here, then here, then here, then here. In particular, these are just rotations. Similarly, this configuration can move around here by action of these groups and so on. So, however, there is no way of taking this configuration to this configuration using any element of the group. So basically, what we have done is we have set up these sorts of equivalence classes, where each equivalence class refers to a particular object, and each figure in an equivalence class is a figure corresponding to that object. There are multiple figures corresponding to each object. For example, this object, there's only one figure to it. This object, there are two figures to it, and all others there are four. These two, there's one, this is two, and all others you have four distinct figures corresponding to your object. So our question of counting the number of objects or distinct figures, I mean distinct up to this action by G, essentially boils down to asking how many equivalence classes there are. And these equivalence classes have a special name. They are called orbits. So you take one, you apply by group, you go there, you apply by group, you go there, you apply by, so you rotate, you go there, you rotate, you go there, rotate, you go there, come back. It's somewhat like an orbit. It's mathematicians and their names, but these are called orbits. So the new question is, which is exactly the same question, is how many orbits are there corresponding to a given action of a group on a set like this. Okay, I hope this part was clear. If, by the way, if at any point you have questions, as you have done before, please stop me immediately. Okay. Well, let's look at some naive guesses. You can just say, okay, the cardinality of X, the total number of figures, that's the number of orbits. You will be overshooting because there are many figures which correspond to the same orbit. So in this case, this answer would be 16, but here this is 6. Or you can do another thing. You can say, all right, since there are up to 4 figures corresponding to the same object, I can divide by 4. I can just look at mod X over mod G. But this would be too much of a correction. This will undershoot, because had it been the case that all figures all objects had 4 figures corresponding to them, this would be correct. But it's not the case, right? These guys only have 1, this guy has 2. So now you're doing an overcorrection, you're undershooting. And the correct answer, as we had described before, is given by Burnside's lemma, which just says that the number of orbits, there's this wonderful expression for it. It's 1 over mod g, so we had this part right, but mod x is replaced by something larger. So you sum over all of these symmetries and you look at the number of fixed, like G symmetric figures, that is number of figures which are invariant under the symmetry of G, and you take an average of those. So if I write this one heuristically, number of objects is equal to the average number of symmetrical figures. Okay, and this is Burnside's lemma. Well, now we wish to prove the Burnside's lemma, and to do that we make us another small definition. We talked about orbits, and now we define something called a stabilizer. A stabilizer is sort of the dual concept for this guy. This says that you fix a figure now, and what group, what symmetries is this figure symmetrical with respect to? In other words, what G in this group of symmetries are there, says that G dot X would be G. For example, I have not included an example, but let's say you have this one. Okay, this is symmetrical under identity, of course. Rotation by 180 also preserves it, and that's it. There's nothing else you can do. You cannot rotate by 90 and keep it fixed. Okay, so this will be the stabilizer corresponding to this set X. All right. So now we proceed for the formal proof of Burnside's lemma, and the first step would be choosing a set of representatives. That is, from you do one thing, from each of these orbits, pick one. Doesn't matter which one, just pick one. See, this one, the yellow might not be visible. So let me change the color to a more obnoxious color. There we go. This one, pick this one, my wish, this one, and say this one. So from each orbit, I picked a figure. In particular, I picked a figure for each distinct object. All right, and call it XR. So XR is okay. I've written it down. It's a set of representative pictures. And what is the cardinality of XR? That is precisely the number of orbits, because I've picked one from each.
Excuse me.
Yeah, go on.
In the definition of stabilizer of x, I am confused. G dot x equals G.
Oh, it should be X. Sorry, you're right. Absolutely right.
Okay.
G dot X is X. Yeah, X remains invariant under G. Sorry about that. Yeah. So, yeah. Now we have these collection of representatives. We look at this multi-set. G dot X, for you take all the symmetries, you take these representative elements and you act every single symmetry on them. Okay, that gives you a collection. Now there can be multiple elements in the collection, and we don't want to lose them. That's why instead of defining a set, we define a multi-set, so that the same figure can appear multiple times, and we'll just call it the multiplicity of that figure. Okay. So evidently every single figure comes up. Why? Because by definition, if any figure is in some orbit, and you take the representative of that orbit and you multiply by elements of the group, or sorry, you act by elements of the group, and you get to, so this is say X, and this is your representative Y. So to get from Y to X, you rotate twice. Okay. So yeah, you look at this multiset and every single element is there. But the question is, how many times does it occur? Some figures make appear multiple times and some figures will appear multiple times. So well, let mx be the multiplicity of x in S. Then on one hand, the size of S is just xr times g, because that's how we have constructed it. The size of xr times the size of g. And on the other hand, it's just the summation of these multiplicities. In particular, if you want to find the cardinality of xr, you get it's 1 over mod g times the sum of multiplicities. It's the average, and not the average in this sense. So it's the sum over multiplicities divided by g, size of g. So we have gotten this 1 over mod g outside. But there are still two problems. This summation is not over g, it's over x. And what the hell is this mx? We don't really understand this multiplicities. So let's try and understand the multiplicities first. So fix x, okay? Pick an x. And we want to find what m sub x really is. So take y from this our collection of representatives that we had, and take the y corresponding to x which lies in the same orbit as x. Okay. Then you can find, then there is just some g1 such that x equals g1 dot y. Right? Some group element you can move by that, and you would get y. It's x and y is symmetrical. That's the whole point of an orbit. But now look at this sort of expression. H dot x, if I give you something which fixes x, then hy1. So if I say h is a stabilizer of x, so h stabilizes x, then h into g1 takes y to x, and vice versa. So if h into g1 takes y to x, you can show that h takes x to x, because g1 dot y is x, right? g1 applied on y is just x. So this gives you immediately a one-to-one correspondence between this set of stabilizers and this set. What is this set? This is the set of all group elements which takes y to x. The cardinality of that is the same as the number of group elements which fix x. They're not the same set, the cardinalities are the same. But all we care about are the cardinalities. The cardinalities of this right hand side is precisely the number of times x appears in our multiset, right? Because our multiset was exactly this collection, g dot y and so on. In particular, we get that the multiplicity of x, the number of times a particular figure x appears in our multiset, is precisely the cardinality of the stabilizer of x. And so this was our set. Yeah. For example, let's not give examples here. I hope this part is clear. And the second part, so we have got this, right? We have gotten that the number of orbits is 1 over mod g times summation of x and x of the stabilizers, of the cardinalities of the stabilizers. Now, we still are not there, but this is a very useful trick, is changing the order of summation. Well, the number of stabilizers is precisely just a sum over ones with the condition that g dot x equal to x. So this summation can be written exactly as this summation. With this extra condition, we have put in this extra condition in the index of summation that g dot x must be x. Otherwise, we do not sum that term. Okay. But now we can interchange the sums, right? Instead of summing over g first, we can sum over x first. So we are now just summing over x in x such that g dot x equals x. And the sum over g goes outside. But this sum inside is precisely the number of group elements stabilized by x. Sorry, what am I saying? That's the other one. But the sum inside is precisely the number of figures which are symmetrical with respect to g. That g dot x equal to x, and we get our answer. Okay, so both of these tricks, this comparing cardinalities trick and this interchange of summation trick, these are useful everywhere in combinatorics, group theory, any sort of discrete analysis you're doing, these will come up. So that's why I wanted to show the proof completely, because these tricks are useful. All right, so that completes the proof of Burnside's lemma. And this should be a nice point to ask any question if there is any. If not, okay, let's talk about this for a while. Since we've basically talked about group theory for a while. So let's introduce formally what is a group. Well, groups are precisely designed to mimic the properties of symmetries that we had seen before. For example, what is a group? A group is a set G with a multiplication, with a notion of multiplication inside, such that multiplying any two group elements will give another group element. You can compose symmetries, right? You can rotate by 90 and then flip it, and that's also a symmetry. So these are group elements. So groups must have this property. Also, acting by G2, G3 first. This is a more technical one. It needs to be associative. And other than that, we had seen that do nothing is also an operation. So the groups must have an identity element. And finally, if you can rotate by 90 degrees, you can rotate by minus 90 degrees and come back. That was precisely rotation by 270 degrees, right? So you have this notion of an inverse. So this is what is a definition of a group. And generally groups are used to model these symmetries. And yeah, these are just mathematical abstractions capturing the essential ideas of symmetry. If when you have any object, the number of its symmetries actually form a group. You can just check these 4 properties. Okay, and groups can be made to act on sets, as we had seen before. If you look at our groups, they were acting on the set of figures, right? And the group action should have a couple of properties. First of all, doing nothing should really be doing nothing. So E dot X should be X. It's just like something to make it sensible. That's why we have put it in. And secondly, the multiplication of the group should be the same as composition. So if I want to apply, sorry about that. Oh, just a second. Yeah, I'm back. So if I want to act by G2 and then act by G1, this should be the same as multiplying G1, G2 first and acting them on it. This sort of came automatically in the way we have done it. But yeah, in general, if you're dealing with an abstract group, you have to put this condition in for it to be compatible and make sense. Okay, so I will not go further on this. I just wanted to mention that these are definitions, and these are, I believe, very sensible definitions. And there's a nice quote by Guillermo Moreno, is that groups as men are known by their actions. This might seem weird to you right now, but the way to study groups is one of the ways is to act them on different uh, sets and see how those actions behave. Okay, so these sets could be anything. They could be uh, vector spaces, modules, whatever. But that is one way of studying groups, and that way is very fundamental as we go on in mathematics. But anyway, let's if there are any questions, let me know. Not regarding this part. Okay, this I just wanted to just graze over, but still you can ask. But now we get to the more refined part of our question. Instead of counting the number of objects, can you give me more information? Like, I want to know what sort of objects there are. In particular, can you give me the color combination? Okay, so beat the per. So for example, we had in our original problem, we had one with all 4 colors B and so on. So this information can be captured in a polynomial like this. So we just take r to the power 4 plus r cube b plus twice r square b square because there's two of them, plus rb cube plus b power 4. How do we find such a this polynomial? Okay, here we knew the setup completely, but how on earth do we find this polynomial? Well, the answer is it's exactly the same procedure. In fact, I've copied and pasted this part from the one we had before. So look at the operations by E. What are preserved? Everything is preserved. In particular, this is the polynomial corresponding to E, because there's one figure with all four reds. There are four figures with three reds and one blue, and so on. This is precisely the binomial expansion, right? So this is precisely equal to r plus b to the power 4. Okay. So similarly, if you look at the operation by 90 degrees, the only guys remaining are all red and all blue. So you get r power 4 plus b power 4. This is the polynomial. Okay, by the way, there is this polynomials in r and b. I'm suppressing that p bracket rb there. Similarly, by 270 it's the same, and 180 there's more of them, right? For 180 you get all four red, all four blue, and two red, two blue. Then you get two of them, right? So this is exactly r square plus b square whole square. And just like the miracle we had before, if you look at this new guy, you have the same miracle. That is this 1 over mod g summation pg's. If you, instead of summing the cardinality, sum these polynomials, you get precisely, let's do it. So there are four r to the power 4s here. Okay, you can figure it out that we get precisely the answer that we are looking for. So we get r power 4 plus b power 4 plus r cube b plus b cube r plus twice r square b square. Okay, and this is precisely what we wanted. This is p. There's a name for these polynomials. They're called cycle indexes. Cycle index polynomials. Why are they called so? We'll see very soon. Okay, and this is precisely the p that we wanted. So hey, another surprise. But why is this the case? Well, the proof is also exactly the same. I would let you figure out why this is, because you just use Burnside's lemma, and you'll be able to figure it out. But the trick is to partition this our original figure set of all figures x into these subclasses, figures containing two red and two blue and so on, and use Burnside's lemma on it, and just add them up. Okay. But well, that just differs the problem a little bit. It just says compute these pg's, p sub g's, and then do whatever you are doing. But computing this p sub g in this case was okay. It was easy because you could carry out these operations, and listing x, these x fix e, x fix g wasn't too hard. But in general, that might also be hard. So then how do we go around computing this p sub g? That will be basically the last question of our talk. And for that, we move into, we take a tiny digression into permutations. So what is a permutation? A permutation on a set of, on n elements is just a 1-1 correspondence between this set 1 to n and another set 1 to n. So we could have, say, pi takes 1 to 2, 2 to 3, and 3 to 1. That would be a valid permutation. And such permutations, there's a nice way to pictorially denote them. You just make this sort of an array. You write 1, 2, 3 on top, 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay. So it's something 1 goes to 2, 2 goes to 3, 3 goes to 1. And you can have a larger one, say something like this. It's a permutation on 8 elements. Now, S sub n, this is called the symmetric group. It's the collection of all permutations of n elements. Okay, and you can multiply them and so on. You can compose permutations to get another permutation. So this actually becomes a group. But the main interesting part is for each such permutation, there is something called a cycle decomposition. Look at this permutation right here. Okay, 1 goes to 2, 2 goes to 4, 1 goes to 2, 2 goes to 4, 4 goes to 8, and 8 goes to 1. So you get a cycle like this. Once you have this, you pick the next one which didn't come. So let's say 3. 3 goes to 5, and 5 goes to 3. You get back a cycle. 3 goes to 5, 5 goes to 3. And about 6 and 7, they just stay where they are. Okay. So any such permutation can be written as this sort of a partition, can be any permutation can be partitioned in terms of these cycles. So you have this cycle, you have this cycle, and these two tiny cycles. And there's a nice notation for it. It's this. So a permutation like this, all it says is that 1 goes to 2, 2 goes to 4, 4 goes to 8, 3 goes to 5, 5 goes to 3, and 6 and 7 remain fixed. Okay, and we'll sort of follow this version of putting it. And obviously, every permutation, our initial definition of a permutation was that it's just a one-to-one correspondence between 1 to n and 1 to n. So every permutation has a unique set cycle decomposition. And in fact, we can ask how many cycles of a given size there are. So the number of k cycles in a permutation sigma, let's say sigma is any permutation, doesn't matter. So ck of sigma would denote the number of k cycles in sigma. For instance, in this case, there's 1 4 cycle, there are no 3 cycles, there is 1 2 cycle, and there are 2 1 cycles. Okay, and all the others are 0, ck pi equal to 0 otherwise. All right, in this particular example, what we can do now is maybe go back to our problem just to look at these cycles. Our problem was what all things we could do. We could this was our original setup. We could rotate by 90 degrees. This would correspond to 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. So these are called cyclic permutations if they have one cycle. You get a cyclic permutation like this. Similarly, if you rotate by 270 degrees, it's the same as rotating the other way. So 4 goes to 3, 3 goes to 2, 2 goes to 1, and 1 goes to 4. Okay. And what about the others? Well, a rotation by 180 degrees, all it did was interchange 1 and 3. So 1 went to 3 and 3 went to 1. Again, 2 went to 4 and 4 went to 2. So this is the representation for it. And doing nothing fixes everything. So 1 remains at 1, 2 remains at 2, 3 at 3, 4 at 4. Okay. So I hope this particular cycle decomposition thing is clear. How to do cycle decompositions of permutations. And now let's do one thing. Let's generalize the problem that we had before. Okay. We will say this new problem. You have, let's say y is just the first n elements, just 1 to n. It's just n points. Okay. And G be any group which permutes these elements in some way, shape, or form. What permutations are allowed, we are not specifying, but it's just a group. Okay. And once we, since all it does is permutes n elements, and Sn is the collection of all permutations of n, G is of course contained in Sn. In particular, every element of G is actually a permutation, and so it of course has a cycle decomposition and so on, right? So, and we make G act on this set Y as usual. Okay, and we again want to see how many distinct ways are there to color this Y. So this Y is different from the set of all figures that we had before. Corresponding to this, the set of all figures, X would be equal to all colorings of Y. So you take every single. So you give coloring. you have n vertices, n points, and you give colors to those n points. So another way to denote it would be the set of all functions capital C from this set 1 through n, which is y, to just this set R and B. Okay, this is a set of all colors, and it's the set of all colorings under this. It's the number of distinct such colorings under this action. That's what you want to find. And taking, of course, n equal to 4 and G precisely as before, this was just these guys. Okay, it's 1, 2, 3, 4, 1, 3, 2, 4, these four. Let's call them G1, G2, G3, G4. If you take G as these guys, G1 through G4, this gives us the problem that we had read before it. Okay, we want to classify them according to their color composition, and Polya gave a wonderful procedure for this. So you look at this group of symmetries. Every element in this group is of course a permutation on the n vertices, and define these polynomials Q. Q of Z1 through Zn, it's simply Z1 to the power of Q sub G of this is the number of cycles in G of length 1. Z2 to the power number of cycles in G of length 2, and so on, and define Qz to be an average of these guys. Once you have done that, then computing our polynomials P sub G and the overall polynomial P is just done by substituting R plus B, R square plus B square in terms of Z in place of Z1 and Z2, so on. So if you go back to our previous example, Q of Z1 through Z4, because we had these four group elements, looks like this. So this has 4 cycles, this has 1 4 cycle, this is 4 1 cycles, this has 2 2 cycles, and this is just 1 4 cycle. So this is precisely what you have, and these are exactly the polynomials that we had before. This is P sub E that we had before. This is PR90, PR180, and PR90. So this gives a way of finding these polynomials. Okay. Now let me, since I don't have much time, let me hint at a proof. I won't go into much details. Fix a permutation, like fix an action, a permutation G. All right, and we wish to compute this PGR comma B. Well, what does this permutation do? Let's say this is the permutation. Then it takes 1 to 2, 2 to 4, 4 to 8, 8 to 1, 3 to 5 to 6, and 7 remains as it is. If I have a coloring which is invariant under this particular permutation, what happens? So what sort of coloring can I have? You can easily check that 1 must have the same color as 2. Indeed, all things, all the points in this part of the permutation must have the same color. All of them can either be red or be blue. So in particular, you have something like this, that these 8 colored points are invariant under the action of G, even only if each of these cycles are monochromatic. Well, and how many possibilities are there? And what are the, what is the polynomial which captures such possibilities? Because you're coloring 4 of them with R or 4 of them with B, it's just R to the power 4 plus B power 4 times R cube plus B cube times R plus B. This is the part which I will not justify. It's a nice combinatorial trick to write down these polynomials. You can justify it yourself, and this would be the polynomial corresponding to it. Okay. And the coefficients of a polynomial constructed like this precisely gives us the number of invariant configurations. And this is exactly, so in our case, QG would be Z1 to the power, so there's a 1 cycle, there are no 2 cycles, there is 1 3 cycle, and there is 1 4 cycle, and this is precisely what it corresponds to. Okay. So there's of course nothing special about 2 colors. You can do the same with 3 or more colors. In that case, all you would have to do is plug in R plus B plus G, R squared plus B squared plus G squared, and so on. to each of these uh, uh, these things, Z1, Z2, and so on. And this generalizes to any number of colors. But if I want to go back to our previous problem, how many distinct objects are there? Just put R equal to B equal to 1. That'll add up the coefficients and give you the number of objects. So once you have found this polynomial Q, which it's an easy procedure just to find you just take the average of those polynomials, and those polynomials is just Z1 to the power number of cycles, number of 1 cycles, and so on. So it's an easy procedure to find this capital Q. But once you have done it, you are basically done. Number of distinct objects, just Q of 2 comma 2 comma 2. If there are 2 colors, and if you have k colors, it's just Q of k comma k comma k. Okay, and so that has a nice representation as well. So if Q of Z1 is looks like this, right? So Q of k comma k comma k would simply be replacing each of these Z1 through Zn by k, and that would be k to the power the number of cycles in G. And that is also intuitive because if we go back to our previous case, the same analysis can be carried out. So if you look at this, the number of cycles, so each cycle must be monochromatic. So how many possibilities are there? If I can color each cycle, if I have k colors, well, it's just k to the power number of cycles. So that's precisely what comes up here, and you take an average of that. That's how you get your answer. If just for the last thing, that is precisely what we did when we looked at our second example, the tic-tac-toe example. See, this guy, this rotation had 3 cycles. That's why we had 2 to the power 3 possibilities. This one had 2 to the power 6 possibilities, and so on. So the fact that we had all these powers of 2 was not really a coincidence. It was because we were saying this is 1 over 8 summation 2 to the power number of cycles. Okay. So yeah, that would be my time. I don't have anything more to say at the moment. So are there any questions?
Someone asked a question in the chat.
Yeah, go on.
Can you explain the group action thing?
Group action thing is okay. So group action thing, I mean the whole talk was on group actions. Which part? You mean the definition, right? So
Yeah, correct, correct.
okay. So this is when we say there's an abstract group, we just mean a group with some notion of multiplication. That's all. But really, where does this group come from? We modeled groups as the avatars corresponding to symmetry, as idealizations of symmetry, right? Whenever, so in our case, you would see that, let's say we had a rotation by 90 degrees acting on X, and applying it twice. If I apply rotation by 90, applied on rotation by 90 of X, giving us back X, giving us actually a 180-degree rotation on X. Using this, we sort of said, okay, then rotation by 90 composed with rotation by 90, that is rotation by 180. So we started from a collection of, we started from an way a particular, this collection of symmetries acts on an object, and use that to give a notion of multiplication on our collection of symmetries. We did not explicitly do it, but in the back of my mind at least, this is what was going on. So similarly, if you apply a rotation by 90 degree 3 times, this cube just means it's a product 3 times equals to 70, right? However, sometimes we can start the other way. We have a pre-existing group which has some multiplication inverse and so on and so forth, and we want to define action of this group on a set X? Well, it's just G dot X is another element of X, a capital X. So that's not a problem. But it should have some links to what the group really is, right? In particular, the identity of we demand these two conditions. That is, the identity of the group should actually. Otherwise, it's not the identity. Otherwise, I mean, we want to incorporate some characteristics of the group inside, and if identity does not act trivially, then God help us. That's the first one. And the second one is acting by some G2 and then acting by some G1 on this object X should correspond to really the multiplication G1 times G2 acting on X. Okay. So this just means that composition is the same as multiplication. For our group action. Okay, and that's precisely what we had before. And when constructing we sort of sometimes what we do is what we did here is that we have an action of a collection, a set of symmetries on a set. From that we construct the group. That's one way to go about it. And there this condition is automatic. This is the definition of multiplication. So in that case, so this is automatic. But when you're dealing with an abstract group, you have say some weird group coming from some weird situation with just the definition of groups is quite abstract. You have just a collection of elements and some notion of multiplication and an identity and an inverse. That's all. So then you have to impose this condition for the action to be sensible, so that it should capture some essence of the group. Okay, so these two I believe are quite natural conditions, and there's no other condition put. So this is what is called a group action. Again, I did not want to unnecessarily describe group actions and groups too much, but I thought this was a nice part to introduce a little bit of it. Just these definitions. Okay, and you will see more of this. I don't know whether you will see group actions, but you'll definitely see groups in the talk by Professor Radhika Gupta, which I think is tomorrow. Rinkini, can you confirm? Or maybe.
It is there.
Yeah, I guess it's tomorrow. So, yeah, hopefully this was a very mild, not even an introduction. It was just a mild teaser for group theory, and that it's quite helpful in various things. Any other questions? Hopefully your question was answered, by the way. If not, you can ask more. But
No, I got it.
okay.
Okay. Thank you,
If no
Saraswata.
questions, just one thing, I'll just I have a list of references. That's all. So yeah, have a look at these. This the first book is quite easy to read, and it'll be a very fun read for those of you who had not seen combinatorics properly before. And this also contains these Burnside lemma and Polya counting things. This is a slightly harder book, but it's very rewarding. And this is just a book on algebra for some group theory stuff. Okay. So yeah, that's all I had. Rinkini, sorry for interrupting. Go on.
Yeah, thank you, Saraswata, for such a wonderful talk. Any questions, you guys can refer to him. And I'll just tell you that the next talk is from 1:30, and please make sure to join that talk. Thank you, everyone, for joining.
Thank you for having me.